Hello, we're going to look at the chapter solid state from the point of view of the JEE main and the advanced exam. Now, in the JEE main, not a lot of questions are asked regularly. Even when they are asked, it's mainly stuff like voids, radius ratio, density, and some ideas of Bravais lattices also, which is direct theory. This is what is tested in the mains. So a pretty simple chapter from that point of view. Now look at the JEE advanced exam. In the last few years, specifically in 2018, there was a question on unit cell. Now this was an integer question. 2017 again had an integer question, this time on packing fraction. 2016 had a multiple select answer, it could have more than one correct answer. That was on CCP ideas, radius ratios, packing fraction. Yeah. And 2015 also had an MCQ on unit cell. 2014 did not have any question. So almost asked every year and easy marks. So most of these are direct applications of the basics of solid state, which we'll look at in detail in theory. Well, we'll look at a short theory session and then we'll go on to do some numericals. So stay tuned. Let's quickly go through the theory that you need to solve most numericals in the advanced in the JEE main exam. It's going to be a quick one here because the theory is not a lot. You just need a lot of practice. So starting with, you have different types of solids, a little bit of theory in NCERT that you need to go through. Yeah. The next thing you need to revise is the basic different types of cells. What's a unit cell? What's a lattice? There are two types basically, primitive as well as centered. What you have in front of you is a diagram which you have A, B, C sides of the unit cell and alpha, beta, gamma, the angles that these sides make. Now, depending on these and whether the atoms would be fitted in body centers, face centers, or end centers, you get 14 different Bravais lattices. Now, this idea is not tested a lot in the JEE advanced exam, but in the JEE main exam, questions have been asked just on this basic theory. All right. So, besides this, what you have is, okay, let's look at the different types. Yeah? Let's look at some diagrams now of simple cubic and all of that. So, simple cubic is a primitive type of cell, which means that one unit cell has just one atom. And that would happen if you have these, you see these X's, they're all in 8 corners and together they would give you one atom. The contributions are 1/8 each. Yeah, this contribution idea is probably the most important thing in solid states, and so you can figure out how many atoms are in unit cells, and this will help you solve most of the questions in the advanced exam as well. All right, so on to this. This is simple cubic. So after this, you have body-centered cubic as well as FCC. You see that on your screen. Now, body-centered cubic is very much like a simple cubic. The only extra thing is in the body center, there's one extra atom. FCC, face-centered, is again 8 in the corners. The body center one, the contribution of the one in the center is just 1. Be careful about that. FCC, you have the 8 corner atoms and you have face centers. Each of these have a contribution of half. That's what you see on your screen as well. So a total number of atoms because of in the body-centered cubic is going to be 2. FCC is going to be 4. Yeah, this is something that you will get used to. You don't have to mug it, but you'll get used to it if you do a lot of questions in solid state. All right. The next thing you need to revise is the ideas of edge lengths and how they relate to the radius ratios. So you have that on your screen. Yeah, the simple cubic ratio, the BCC, FCC, R and A. Yeah, how are they related? And what is the nearest neighbor distance? This second part, the nearest neighbor distance, is what you use to derive what's on top in pink. So the derivations are really important. They will help you get all the questions in advance. I guarantee you, if you just know this derivation and also those figures we know before, you'll be able to solve most questions on these ideas in the advanced exam. All right. Some more basics that are really important are the idea of, from 2D packing, how do you even get to 3D packing? So you have layers. Yeah, if you have AB, those type of layers, basically B covers the tetrahedral voids, then you get HCP. Similarly, if you have ABC type of packing, that's called cubic close packing, and there C covers octahedral voids. Octahedral voids, you have 1 per atom, tetrahedral 2 per atom. So coordination number is also goes hand in hand with all of this. Coordination number is 12 for this sort of thing, and the packing fraction is 74 when you have either of these. Yeah, the cubic close packing along with ABA or ABC type of packing. BCC has coordination number of 8. 68% is the packing fraction. This is not close packing. As simple cubic has a coordination number 6, 52.4%, not close packing again. Now these ideas are again for maybe single atoms. If you have a compound, then things get a little bit more tricky because the radius ratios, the packing fraction will be slightly higher, right? Because most of the time, the smaller ion fits into the voids of the lattice that the large ion sits in. Yeah, that's the simple idea you need to know. Okay, just a little bit of a revision of voids again that you need to be sure of. Tetrahedral voids, there are 2 on each body diagonal and at a distance of root 3/4a from each corner. Okay, octahedral voids, there's 1 on every edge center and 1 in the body center. The structures of NaCl and all of that. Tetrahedral voids, diamond structures, ZNS and all that. Okay, so ionic solids, you need to revise all of these, mainly for the main exam actually. Sometimes, at least in the last 5 years, nothing has been tested on this idea that you need to know exactly how these solids look like. NaCl, CSCl, ZNS, CaF2. This is more or less of a practice thing that will make sure you know how each atom, whether it's whichever center, face center, body center, or edge center, how they contribute, and also how when atoms go into the voids, how does that contribute, how does that look and all that. More for that practice, this is really important. The radius ratio basically decides the coordination number between the anion and the cation. Density, this is tested a lot in the JEE main exam. So this is something you must know. It's a simple idea. Density is mass by volume. That's all you need to derive this. The only thing you need to be careful is Z effective is the effective number of atoms in each unit cell. All right. Next idea, again, tested more in the JEE main exam as compared to the JEE advanced exam, is the idea of defects. Point defects, there are 2 types, stoichiometric and non-stoichiometric. Non-stoichiometric, the formula changes. Let's go over them one by one. So stoichiometric ones first. We don't look at, there are many other types like, line defects and plane defects, but that's more in materials engineering if you take that later on. Anyway, point defects. You have vacancy and interstitial. Vacancy decreases the density, interstitial increases the density. Both of these are basically non-ionic type of defects. Schottky and Frenkel are ionic defects. Schottky, where you have an equal number of positive and negative ions removed, density does not change. Frenkel is where dislocation, stuff moves into the voids. Again, density does not change. Now for the non-stoichiometric ones, metal excess and metal deficiency. Metal excess has the F center, that provide color, the extra cations. So things like Zn1 plus XO, and metal deficiency is when some of them are lower. So there's less metal than what you expect to be. So things like Fe 0.960. A question was tested long back in the JEE advanced exam based on this, but you could pretty much solve it using the idea of stoichiometry and just basic mass balance. All right. Electrical properties, again, some theory is tested mainly in the main exam. You have conductors, insulators, semiconductors. Doping of semiconductors, that's been tested in the advanced exam as well. Again, not now, but some time back. Basically, P and N type of semiconductors. Magnetic properties, that kind of wraps up this chapter. The last part, the magnetic properties. You have diamagnetism, paramagnetism, ferro, ferri, and anti-ferro. So you see these domain diagrams. This is an easy way to remember it. And the Curie temperature is temperature after which no ferromagnetism exists. A quick thing in the end, this chapter, although very scoring, is probably the basis for the whole of semiconductors. And if you are looking to go into the field of nanotech, this is something you must pay attention to. Nanotech would have applications in electronics or in material engineering, chemical engineering, and even mechanical engineering. So all those simple chapters score marks. Pay a lot of attention to this if you want to get into nanotech later on. And let's get started with some questions. Okay, this is a question where we expected to give a numerical answer. Here's a beautiful cell in front of you, a lot of colors. I'm going to go through what's in the question. You have yttrium, barium, copper, and oxygen. They are marked. You have like the solid blue thing is the yttrium, plus sign is barium, copper is the pink circle, and oxygen is the X. This is the whole unit cell. This is called a perovskite structure. All right, a very interesting thing. It has superconductivity at room temperature. All right. Anyway, so we're asked to find out the formula of this pretty much. If you have some values of A, B, C, D, you need to add it up and give them the examiner the answer. So this is the approach. Well, first thing is you count the individual atoms in the 3 different parts. You have 3 parts there. You need to account for, as usual, the corners, the edges, the face and body centers. So these are the first 2 things. And after that, if you get a whole number just by doing all this, that's great. If not, then you need to make sure you get the whole number. The molecular formula must have a whole number. Okay, so I think let's start with the easy ones. I think yttrium is pretty straightforward. So that's the cell in front of you again. This guy here, this is yttrium. Okay, just one simple thing. So I have 1 yttrium in this entire thing. If I divide into 3 blocks, so to speak, I have block 1, block 2, block 3. So yttrium, I just have just the 1 atom in the second block. Okay, so yeah, let's move on to the next one. I think barium is also pretty straightforward, right? Because it's only in the entire block by itself. That's why I'm saying it's simple. Yeah, it's not shared between two blocks or anything of that sort. What am I talking about? This plus right here and this plus right here. Yeah, so again, block 1, 2, and 3, and I have 2 atoms of barium. Yeah. Okay, so far so good. Let's look at the next one. Copper. Now things get interesting when we look at copper. Why is that? The circles, pink circles, nice pink circles. If I start counting it, just the circles, how many do I have? I have 4 in this layer, block 1, okay, block 2, block 3, 4 in the top layer here, 4 in the bottom layer over here, 4 more here, 4 more here. Now, just adding these guys up together doesn't seem like the sensible thing to do. Why is that? Because the contributions are not all the same. If I just simply add it up, I get the number 16, okay, but is this useful in any way? Because see, the top ones have a contribution of say 1/8, just like any corner atom would, right? But these guys here, they're shared between 2 of them, yeah, between block 1 and block 2. Yeah, I'm talking about this plane here right now. So both of these will now have a contribution to 1/4 and not 1/8, yeah, twice of 1/8 basically. Same with this one over here, 1/4. And this one's again 1/8, the contribution. I'm just talking about the contribution wise. That's why I'm saying just counting the whole thing as 16 is not very useful because they have different contributions and there's a chance of making errors. Sure, if you're confident about this, you can also do this if you remember that these contributions are different from the first layer and the last layer, which is, you know, this over here and this one over here. You can do that if you're confident. But I would say, you know, let's not do this. There's a better way of doing this. Let me erase all of this and tell you what makes more sense to me and what's the foolproof way of doing it. Yeah, foolproof meaning there's no chance of making errors. That would be take these blocks separately. Yeah, block 1, block 2, block 3. Count them entirely as their different cells because you're comfortable with the idea of you know, what a cell looks like, what a contribution of a corner atom is, or face center atom is, a body center in a particular cell. If the one block was one cell, that's what I'm asking you to consider. If you do that, then you have say you have 8 in the first cell. Yeah, 4 in the top layer, 4 in this layer. Second block again, I have 8. How's that? 4 on the top layer here, 4 more in the bottom layer. I know I'm counting it again, but this is a safer thing to do than to figure out the different all the different type of contributions because of the mixed sharing, right? Let's do it this way. And then again, third block, there you go, 8 again. This makes life a lot easier because now totally I have 24, 8 into 3, that's right, 24. And the contributions are 1/8 each. So I have 3 copper atoms. I'm sure this is correct, okay? Because of the number of times I've solved a single cell idea and I know that there's 1/8 contribution. So let's do it like this. And this way you're not going to make a mistake. Okay, so copper has a contribution and gives you 3 atoms inside it, all right? Inside the perovskite thing. Let's do oxygen now. I think this is going to be a breeze, yeah? Now the reason why I did that, you'll see why I did that now, because oxygen gets a little bit complicated, yeah? So what happens is oxygen, I'm going to give you a clue. Obviously, we're going to do the exact same thing, you know, the same thing. Block 1, block 2, block 3, divide them up together, sum them up. If you did anything else, look at this. Here, all the edge centers are occupied, yeah, over here, all of the edge centers. But in this one, not all, yeah. You see these are empty. I'm just marking these. There's nothing here. So there again are more chances of us making errors. So it's best to do the whole thing one at a time. So again here, all edge centers, and here, yeah, some of them not so much. Okay, so let's count here. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, not all here either, yeah. Oh, I see. I made a mistake just by explaining it. Just look carefully. There's nothing here. There's nothing here. So there again, a chance of making a mistake, which I luckily spotted. Yeah, we're not doing that. Let's count. Let's just use our. Let's do it step by step. Let's count. All right, I have 1, 2, 2 in the top plane, in the middle plane, or you know, this if this were a plane. I hope you can see that. Yeah, that. There are 4 here, and in this one there are 4 here. That makes a total of what? How much? That's 10. Okay. Ooh, big line. Let me erase that. Okay. Yeah. Okay. So there are 10 over here. What about this middle guy in this block 2? How many do I have here? Well, 4 there and 4 more here. So here I have 8. Okay. The last one looks very similar to the first one. It's just flipped the other way. So here I have 4 again. The middle plane, if I were to draw it, yeah, this is going to have 4 more. Let me erase these words. Edge is sticking out as a sore. Okay, so I have 4 more over here. I have 2 over here. So this again is 10. Easy. Now the rest of stuff is really simple because I have now a total of 28. Yeah, let me write that here. More space on this side. So I have 28 oxygen. Oxygen? Yeah, oxygen. All right. And what's the contribution? Yeah, it's edge center. So 1 to 1 by 4. There you go. I have 7 of these guys. If you did anything else, if you're really good at it, sure, whatever you're confident with. But I'm just giving you a foolproof way of not making mistakes for sure. Although I made a mistake by saying, oh, all the edges are, but when I saw carefully, nothing here, and nothing here. Yeah. So be careful. Just do it from the basics, count them. You have this. And yeah, the next step is very doable. All I need to do is get the overall formula now. How much of yttrium do I have? Oh, the formula of yttrium is Ya. YT? Let's check. Is it YT? I think it's YT. All right. So this is basically 1. Barium was 2. Copper was how many? Copper was, let's scroll back up. How much of copper did we have? Copper was 3 and oxygen was 7. Okay. Copper was 3, oxygen 7. So what I have here is x plus y plus z plus m. Okay. This is going to be simply 1 plus 2 plus 3 plus 7. That's 10 and 3. That's 13. Lucky number 13. That's your answer right there. Okay. So, yeah, this is the answer. The only thing that you need to take care of, so to speak, is the contributions bit. Yeah. Don't mug it blindly. You realize here that there were 3 units, 3 blocks that made up this unit cell. So we did something different. We treated them each as unit cells and said, let's count them all and then multiply by 1 by 8. Because that's the thing most students are going to be familiar with. If you're confident and you realize that, hey, you know what? Now this atom is being shared by 2 of them, the con atom, instead of 1. So now it will contribute to 1/4 and not 1/8. Sure, go ahead and do that. This is a foolproof way of doing it. Answer is 13. Here's a question that expects a numerical answer. You have a cell and some operation is performed on it. Yeah, there's a molecular formula that has as it is described, and then you make a change to it. You remove some edge atoms, then the molecular formula, whatever the new one is, you need to add up the old and the new one and report that as the answer. So let's get started. What's the approach here? All right, so just form the base cell as described. Okay, that's the first one. And then we're going to follow instructions and remove just the edge atoms in this case. Account for the number of atoms removed with the relevant ideas of the, whether you're removing a face center atom or an edge center or all of that, and what the contributions would be. Finally, find out the molecular formula. Sometimes you may get fractional things in. You need to make sure that you have a molecular formula. Molecular formulas don't have fractions. That's the only thing you need to be careful about, the last part. Let's see. Let's get started. So here it is. I've written down the conditions. Let me go ahead and draw this. Try to draw this. X is in the corners. That's the first condition that's given to me. Let me do that. All the X's being marked here. And then O is in the edge centers. Oh, I missed out an X. Hold on. There's another X. Yeah, one more. Yeah, there are 8 corners. 8, not 6 or 7. Okay. And edge centers. Let's do that next. Edge centers. Am I getting them all? It's not missing. So I have one. Okay. 12. Do I have 12? Yeah, all edge centers accounted for. And 1 Y in the body center. This is it. This is the setup for our origin atom. Okay, let's see. So what happens when you are trying to figure out X, Y, and oxygen? Yeah, it's a simple thing. I drew this, but I think if you're comfortable with this, you'll be able to do this part right away. So there's going to be how many? There's going to be like how much? 1 Y, right? That's in the center. X is going to be 1 because you have 8 and each contributes to 1 by 8. That's a corner atom. So that's going to be equal to 1 again. That's 1X. And X, right? Yeah, X. All right. X marks the corners. And O, okay, for consistency's sake, let me just do that. Number first, I have 12, each of which contributes to 1/4. Remember the edge? 4 edges together would. All right. So that's 3 O's. There you go. So this is the number I have here. So X, this is an 8, this is a 1, and this is 12. And I get X, A, Y, B, O, C to be what? X1, Y1, XYO3 or just XYO3. Yeah, that's the same thing. Sum them all up. A plus B plus C is 5. Yeah, this one's straightforward. Very doable. Let's see what we got to do next. We got to remove 2 edge centers. Okay, I'm going to quickly draw that again. Not miss out any x's this time. X, 8 corners. There you go. Okay. What else was there? At edge centers, I'm going to remove 2, right? Okay, let's skip these 2 on purpose. This is not a mistake. The question asked for this. We remove. There you go. Is that correct? No, 2 more. That was on purpose. And yeah, another guy in the center. The Y stays there. What happens now? What changed? The only thing that changes is 2 edge centers are removed, right? So now I will still have 8 x's, corners, 1 y, body center. I'm going to have 10 here. Not even doing any math. It's 12. I remove 2. So there you go. Now here, this is what? This is 1. This is 1. This is 2.5. So x, y, z. X, X, Y, Y, O, and Z is going to be what? This is going to be X, Y, Z, 2.5. This is not the molecular formula. You cannot have a molecular formula. There's a fraction. So you need to get it to a whole number, right? So you multiply the whole thing with 2. That's my way of writing it. So this becomes X, that looks like Y, X2, Y2, Z5. That's the only trick in this question. Do this carefully. Yeah, that's it. Need to make sure you get full things here. So x plus 5 plus z is now simply going to be 2 plus 2 plus 5, which is 9. What's my answer? I need to add them all up, right? X plus 5 plus z, as well as a plus b plus c. So how much is a plus b plus c? Did I forget that? Wait, let me see. I have an amazing memory. There you go. A plus b plus c is 5. And well, sum the rest of them up. That's 5 plus 9, which is 14. And that's your answer right here. The only thing this question tested was your ability to figure out that the molecular formula cannot have fractional numbers in them. Okay, simple steps to follow an integer answer, which was 14 in this case. Okay, this question can have more than one correct answer. Okay, I'm going to read this out to you first. So you have some amount of semiconductor material, XY, given to us, and its mass is also given, 21.6 grams. And the electronic configuration of X is some noble gas times NS2. Looks like it's a D block element. And then the material is doped with some other element, Z. Now this replaces an equivalent amount of Y, and now Z has a different configuration. Yeah, let's go. NS something, N minus 1 D something, N minus 2 P something. Okay, so let's see what we can do. The options talk about X being a metal, specifically cadmium or copper, and HCP and CCP, and whether the semiconductor formed is N-type or P-type. Okay, let's look at the approach first. All right, let's get started. So what's your approach going to be? Firstly, figure out the molar mass. Okay, once you have the molar mass, then you can then get the identity of X. How's that? We'll see. It's quite doable. We can use the electronic configuration given to us in the question as well as the molar mass. All right, these 2 things will help us tremendously. Then once we get X, we can get the identity of Y, its molar mass. We can do these 2 things. Compare this to the dopant that is put in. Yeah, that's the thing. If I'm replacing some amount of Y with Z, if Z has more electrons in the valence shell than Y, then it's going to be an N-type. Otherwise, if it has fewer electrons, it's going to be P-type. That's the key idea of figuring out semiconductor with N or P-type. So let's get started. I think the first part is pretty direct. Yeah, it's just a little bit of stoichiometry. What's the molar mass of XY? We've been given it's, you have 21.6 grams is the mass, and the number of moles is what? 0.15 moles? Yeah, let me just put that down. I think this is an easy thing. Okay, so you can divide it by 3, right? So yeah, you get 0.0. Pen, please write, don't hang. Oh, there you go. This is 0.05 and this is 7.2. Okay. You divide them both, you get 144 gram per mole. Yeah, that's the mass, molar mass of XY. Did I get the units right? Yeah, gram mole, so this makes sense. X, what can X be? Well, okay, this is NS2, N minus 1, D, 10. Now, can copper have this? Copper is like, copper would probably be NS1, 3D10. Okay, if I'm putting the number 3, might as well put what N here is, right? So this is 4S1, 3D10. That's copper. So it can't be copper because this is more like a zinc-like element, right? If I have this configuration, it's more like zinc. So cadmium is the most likely guy here. Does this mean I can mark the first option be correct? Not sure, because there's some packing element there too, right? Packing idea. We'll see. We'll get to that later. We'll see about the answer later. I'm kind of sure right now, not kind of, I'm dead sure that it's cadmium, yeah, and not copper in this case. So once I have that this is cadmium, the mass examiner has been nice. They've given us the mass to be 112.4 gram per mole. They've given us this mass. So now what can I do? Yeah, I think I can just get the mass of Y now, and its identity 2. So I just subtract these two. So Y is going to be what? It's simply 144 minus, what was that? How much did I get here? It's 112.4, right? The next step is a dopant. That's what you see on your screen. Yeah, don't get distracted by that. This is gram per mole. This is also gram per mole. I know I like writing units. I can't help that. I think you should too. You should always write units down. This is 32. Yeah, it's a little less than 32. It's 31.6. So it's almost equal to 32, which is basically the mass of sulfur. The reason why the mass could be lower than what you expect it to be is probably because of defects. Yeah, this is a real crystal. CDS is what we are going towards. I think this is CDS. I'm almost certain about this. What about the dopant? Dopant is some noble gas, NS2, N-1D, and N-2P5. Now, P5 is a halogen. This is definitely a halogen. And this means that this can be what? I think this has a D block thing, right? So it cannot be fluorine. I think it can be, and yeah, chlorine. Obviously, these two are out. What can be? I think it could be bromine or iodine. Most of the time, if you read up a bit, this is most likely bromine. Could also be iodine according to what the question is saying, but yeah, most likely this element is bromine that it's doped with. And what do we have here? So compared to Y was what? Y is sulfur, right? This has a P4 configuration. P4, right? Yeah, it should be similar to oxygen. That's my idea. That's the idea I'm using here. So this has this, and the dopant has a P5 configuration. That's what I'm writing here. So this has one more electron than what S had in its valence shell, which means that this becomes an N-type semiconductor. So this answer is sure. I'm going to mark this right away. This is conductor, spelling of conductor. Wait, I get confused. I'm really bad at spelling. It's okay. I hope this one's right. So N-type semiconductor for sure. What about the other options? It's not P-type, it's N-type. Let's mark that right away. That one's correct. What about the other thing? We also discovered it was cadmium and not copper. But what about HCP? How do I know if it's HCP or not? Here's the thing, right? The question says that you have the packing fraction of, we conveniently did not talk about that till now, but the packing fraction of this X, yeah, is 0.74. Now, this doesn't help you much unless you just know the theory. Because here's the thing. Both CCP, pen's acting up again. The CCP and HCP, both of them have a packing fraction of 0.74. Why is that? Because they're both close packing. What's close packing? Remember the whole idea of A, B, and like ABC layers? Yeah, a little bit of theory. So this one's CCP and this one's HCP. The packing is going to be the same. All you're doing is you're arranging the layers in different ways, but the space between the layers is going to be the same. So the packing fraction for both of them is going to be 0.74. So that's a little bit of theory. You know for sure it's cadmium, but it is HCP and not CCP. If you're not sure about this, it's okay. It's a multiple correct answer. You can just mark N-type and get away with it. Because you know what, the examiner could mess with you and the examiner could have given that option to be cadmium CCP, and you could have happily marked that correctly because you know that 0.74 is the packing fraction of CCP, but it's also the packing fraction of HCP. So yeah, be careful about that one. So this one's correct. This happens to be correct, but B, this is just giving you a lesson that only mark things you're absolutely sure about. All right. So what are the answers? Yeah, these two options that tell you that cadmium is your compound, is your element, and it has HCP packing, as well as that this is an N-type semiconductor after it's doped by the halogen. Here's a question that can have more than one correct answer. Now, as usual, we have a unit cell, and M, A, B, and C are all occupying some parts of it. What we need to do is Yeah, the examiner is being interesting. You need to remove a plane or a line and see how the ratio of C's to A is and what is the sum of A and B when in the molecular formula. Yeah, just be careful. It's a molecular formula that we are talking about. So what's the approach going to be? Now, as usual, the first thing you have to do is form the base cell as described. We'll do that. After that, we just follow instructions one at a time. We'll remove a plane, do that carefully, remove a line, whatever that is. We'll see how that works out. And then we need to remove the relevant atoms and their contributions also. Okay, so you get some total number of atoms, you subtract the kind of atoms that you remove and their relevant contributions also. So we'll do that slowly. Yeah, this is a bit tricky if you're not familiar with this sort of thing. And in the end, calculate the molecular formula. If you get some sort of fractions, no go. Convert them to whole numbers. Really important idea. Okay, let's get started. First thing, M. Okay, this is the nice empty cell. All the things are given here. M is in the body center, A is in the corner, B is the edge center, C is the face center. Okay, we have a work cut out for us. Let's do this. M is in the body center, A is in the corner. Let me put 8. A is right there. Okay, where does B go? B is on edge centers, so I should have 12 of these, right? Let me put them out. Do I have all? Last layer remaining. Let me draw that quickly. There you go, 12 B's. And C is in the face centers. It's going to get mucky. Let me just draw this line for my reference. So C would be somewhere here, these two faces, here, this face here, this face here, this face here, and this face here. This is 6 C's. Don't worry, I'm going to give you a nice, beautiful diagram to look at, but this is how you would draw it, okay? So onto your nice, beautiful diagram. There you go, more color and all of that. Okay, so what happens? What's the formula going to be like for this guy here? So M, there's just 1 in the body center, right? So this is 1, nothing to do here. A, there are 8 of them, each contributes to 1/8. Corner atom, simple stuff. So this is 1 again. B, we have 12, standard stuff again, each contributes to 1/4. So you have 3 of these. C, face centers, you have 6 of these, each contributes to half. You have to be careful about this one. So yeah, that's what you have here. So the formula now is going to be what? M, A, B, 3, C, 3. Did I get that right? Yep. Okay. Examiner doesn't care for this much, this one. But what comes next is important. So you need this for that. So no questions asked from this exact formula. But what we need to do is draw plane diagonally. And for our convenience, I've written down the things. Is this right? 1, 1, 3, and 3? Yeah, that's what we got to. I'm just comparing these numbers we have here. Okay, so a plane is drawn diagonally and all the atoms along the plane vanish. Drama. So, how do I draw a diagonal plane? Let me do that. There's going to be, we connect these two A's here. These two A's, and this dotted line kind of becomes solid. This one becomes solid. That's what happens. Everything along this disappears. Let me use my surgical tools to remove all these atoms. Yeah, there you go. Oops. Yeah, so far so good. Okay, there's a small A remaining, but you get the picture. Let me try to remove that. Oh god, the whole thing destroyed. No, it's not. Just do that. Okay. This goes, this goes, this goes. Okay, so what did we remove? What's remaining? Let's write down. Let's do some accounting. Okay. Oh, how could I forget this? The M, that's in the that line, yeah? That would lie along this wonderful line over here if I were to draw this. This is the body diagonal. Let me make a solid line there. That's the body diagonal, and M was right over here. So I did remove that as well. Yeah, almost missed that one. Okay, so I get minus 1M. That's an easy one. What about A? I remove 4 A's, right? So minus 4 A's, each contributed 1/8. Just writing it as we'll do the calculation. Don't worry, calculations is not that big deal. Let's count first. Make sure we don't miss anything. What about the B's? What happened to the B's? 2 B's went away. Okay, what is the contribution? 1/4 each, right? Okay, so let me write that. And C's, anything happened to C there? C's. Oh yeah, these two face centers. So minus 2C. Oh, so place for that. Let me do that. Okay, so minus 2 and into half was the contribution C. So that gives me no M. 1 minus, this is 1/2, right? So 1 minus 1/2, this is half A. And what is this going to be equal to? This is 3 minus 1/2. That's 3 minus 1/2 is 5/2, right? Okay, this is 5/2. And what is this? This is 3 minus 1. So this is 2. So what I have now, formula now I have is, poor m's gone away. Let's have A, so that's A half, B 5 by 2, and C 2. Interesting. Let's just check. It's really important to check these sort of things. If I missed anything out, did I draw this right? Sure. Yeah, the body plane. I'm just going to kind of make this even more messy by highlighting this. Okay, so yeah, this is definitely was the body plane. I removed the centers over here, the C's, yeah, the face center, the marking X is there. I'll mark all the atoms I removed as X. Okay, I removed these corners, these are all A's, and I removed these two edges, which were both of these. Yeah, I think my accounting was all right. Again, 1M, the center circle thing goes away. 4 A's, these were corners. Let me write that somewhere. Corners. And this B was what? This was edge. 2 edges that we removed. And C's were face centers. And yeah, this is a body center. Okay, I know this seems silly, but it's really important to make sure that you don't make errors. This is a very straightforward question. If you just do this, put your head down to it like horse binders and get on with it. Okay, so this is it. This is the deal. But here's one thing. These are all fractions. I need to get, I can't have fractions in my thing, right? So I need to multiply the entire thing by 2. So I have A, B 5, and C 4. So now this is the molecular formula of this compound when you remove everything along the plane, the diagonal plane. Okay, the ratio of C by A. Let me see, what's this? A, B 5, C 4, right? Let me write that. So it's A, B 5, C 4. Okay, what's the ratio of C is to A? This is going to be simply 4, right? So this ratio is 4. That's one of the options. Yeah, okay. We're getting somewhere. That one's correct. What about A plus B? They ask you to find out what is small a plus small b. Actually, this should be small, big, I think. Yeah, let's for consistency's sake, let's do small, because C and A, capital C are the number of atoms in the unit cell, and small a, C small a were in the whole formula, right? So let's, for consistency's sake, keep it there. A plus B is 6. Oops, we have 8, right? That's the option. The option says 8. So that was incorrect. So the first one's correct, and this option, well, our calculation is correct. Our calculation is 6, but the option says 8. So nope, that was not correct. Okay, so that was it. We just, got right down to it. Just made sure that we didn't make any errors. Cross-check, always double check. And I think that one's correct. Those were, yeah, we're almost halfway there. Pretty much, a little more than halfway there. Let's do this. This one's, I think, a little bit easier if you did that. That was a little bit more complicated. You need to draw a line along any edge. Any edge and edge. Let's see. Are all? Oh, yeah. All edges are identical. Okay, I'm just going to write that down here because that's really important. All edges are identical. So I can remove any edge. Let's see, which one do I want to remove? All right, I'll remove this one because I think this is easier for me to draw. Straight line. Yay, there we go. Straight line. Okay. Surgical precision tools to remove these atoms. Oh my God, that A just never. There you go. Oh yeah, all of them go away. So what's going away? 2 corners. Mark them as X. These 3 went away, right? So M, no change. Okay, no change in M. So I'm just going to leave it as is. Nothing happens in M. Okay. Triple equal to for some reason. Okay, minus 2A. Each of this has a contribution to 1/8, right? So this is minus 1 by 4. Wow, this is going to look messy, right? Oh God. Okay, let's see. And what about this this guy here? B. B is what? B is just 1. So minus 1B. Each contributes to 1/4. This is also minus 1 by 4. And did I miss anything? C's? No, nothing happening to C. So C stays as is. There's something fishy here. I feel like, no, this seems okay. So what I have here, B is basically 1/4 minus 1 by 4. So this is 3 minus, okay, let's do this math. This is, how much is that? 1 minus 1 by 4 is 3/4. I have 3/4 of A, 1M, and how much of B do I have? B is 3 minus 1 by 4. Okay, that's 12, 11 by 4. Did I get that right? 11 by 4. Does that make sense? That's how much of B I have, and C stays as is. Yeah, again, for consistency's sake, let me just put in triple equal to sign over there. Okay, so nothing changes. Funny numbers. Wow. Okay, this is going to look interesting. What do I have here? I have M, A3 by 4, B11 by 4, nasty numbers, and C3. Okay. So C did not change. Let's just double check if what we did was right or not. Okay. Edge, any edge, whichever edge I pick, whether it's this one or this one or this one, any one. All that's going to go is one B atom and two A atoms. Now, each B atoms contributes to how much? 1/4 of an actual atom, right? Each A atom contributes to 1/8. That's why I've put these numbers down here. 2 times this and minus 1 times this. So the maths are correct. Let me check that again. 3 into 4 is 12. 12 minus 1 is 11 by 4. Yeah, sure. This one's correct. This one's simple. 1 minus 1 by 4, 3 by 4. Okay, cool. So these are math. This is correct as well. This is what I get, and I need to get a whole number, right? Okay, let's do that on top over here. I still have some space. This is going to be, I'm multiplying everything with 4. So I have M4, A3, B11, and what do I have here? I have C12. Interesting. So A plus B, okay, let's do, because that's the easy one, right? Scroll down. I have a lot of space. M4, A3, let me try to remember that. What did I get? Oh, it's already here. I don't have to remember it. M4, A3, B11, C12. Funny thing. Okay, this is not probably, you're not going to get actual compound layers. I know this sounds theoretical. Anyway, so this is what you get. And C by A ratio, small c, small a. C is to A would be 12 by 3, which is still 4. Interesting. I changed things up. The ratio here kind of, it's interesting because initially in the first thing, let's look at that. Although number of C didn't change over here, number of C changed here. And in this first question, first part here, number of C, obviously this is the main thing. So the base thing we started off with. Here the ratio was 3:1. Here we changed some things. We removed A, B, and C, and we got the ratio to be 4. And here, again, we get the ratio to be, what do we get it here? Here also the ratio is 4. Interesting, right? Although we didn't mess with C at all in this case. Yeah, here we only removed A and B. So cool, maths can be pretty interesting. Anyway, moving on. What is A plus B? A plus B is in this case, so A plus B is simply 14, which is what is in one of the options. So yeah, both of these are correct. I know this seems like a tedious thing to do, and the goal was for this sort of question is to get you used to anything the examiner wants to do, however funny it may seem, however improbable it may seem. But hey, you know what? No stress. We can figure it out, and that's what we are here for. So these are the correct options. We have 3 correct answers, and one of them is not correct. The A plus B for the first one was incorrect. Rest of the 3 are good to go. There you go. Multiple correct answers, and they are on your screen right now. Okay, numerical answer question again. You have 4 larger spheres and tiny spheres kind of squished in between them, and this length over here is given to us to be 4 into 10 power minus 8 centimeter. And we need to find out the radius of this tiny sphere, x into 10 power minus 8 centimeter. We need to find what that x value is. What's the approach to a question like this? Well, first thing is, if you recognize that this is same as an octahedral hole. Yeah, if you do 2D packing, then there's an octahedral hole. In 3D, this would be CCP or HCP, either way. Yeah, one of those things. But this tiny thing here, this is an octahedral hole. Anyway, so you just need to find a relation between small r and capital R and from this diagram. Oh, what's capital R? Well, just half of this, right? This guy here is R. You've been given this. So R is equal to 2 into 10 power minus 8 centimeter. We'll substitute stuff right in the end. Let's do a simple math calculation. Yeah. Here, I've now put a nice pink square over here. I've split that in half and got triangles. So we can use the Pythagoras theorem here. That's the goal. Yeah. Once we do that, we'll be able to relate R, capital R and small r. How's that? Well, look at this. The hypotenuse over here, there's an R, this one's R, and this is simply 2R, right? And this entire thing, this is 2R, obviously. And this thing is 2R as well. So there you go. What does Pythagoras theorem tell us? That the hypotenuse square is equal to AB square plus BC square, right? That's what you get from Pythagoras theorem. There you go, just substitute. So 2R plus 2R small r capital R whole square is equal to, what is this? This is going to be, okay, let me write that down. 2R whole square plus 2R whole square. This is a simple way to do this here. Let me show you. You get this. Easy math right here. Okay. Now, if you go ahead and expand it, life is going to become really miserable. Don't do that. Just take root here. That's the only trick if there's any in this question. Okay. First thing was use Pythagoras theorem and do this. So don't expand this. It becomes a little annoying if you do that. Just take a root here right away. What you get is 2r plus 2r is equal to, what is this? 2 root 2r. We ignore the negative value because that does not make sense. Yeah. If we keep the capital value, this then 2 root 2 is greater than 2r, you get a negative thing. So yeah, math stuff, ignore the negative thing when we take a root of this entire expression, both on the left hand side and the right hand side. Yeah, let me write it properly, otherwise the maths guys are going to have a fit. Let's do this. Yeah, that's the right way of writing it. Okay. Yeah, there we go. So what do we have here? Okay, I can take things to one side now. Small r, let's cancel out the 2's. Small r is simply root 2 minus 1 times capital R. And this is just 0.414 times capital R. Yeah, there you go. All you need to substitute this value. I'm going to let you do this on your own. Yeah, this is a simple thing. R is, what is this? This is 2 into 10 power minus 8. Oh, we don't need the 10 power minus 8, right? You just need to report it in those terms. Times 0.414, which is 0.828. And wait, hold on. But this is into 10 power minus 8. Yeah? We need to report the answer as what? What is the question saying? The question says x into 10 power 8, not minus 8. Okay, yeah, so that's the answer. You mark the answer as 0.828. Always check what the answers the question is asking for. Don't make a mistake in the hurry and, mess up this in the last step. So just check. Always double check. That's the answer right here, 0.828.
For more videos and live lectures on the JEE, click on the subscribe button now.